Good evening, everyone. Good afternoon, I should say. We are on directional derivatives, which is nice. This stuff is not in the test, and it's not due until next Sunday. But it's good to get a head start. It means that we can spend more time on some of the other topics when they come up. Last time we looked at how do you find what's called a directional derivative of a function in a given direction where the direction is given by an angle. So I think as an overlap, I should do one of those. So suppose we have a function f of x, y, and it's x squared, take away e to the y, right? And suppose we are interested in at the point 1, 1. I'll make it 1, 0, that's easier. Right, at the point 1, 0, we are interested in finding the directional derivative when theta is, say, pi upon 4. So first thing we do is we use that angle to get the unit vector. And if we use our unit circle and we find pi upon 4, and we can just basically use the coordinates to represent the x and y component. That's a quick way of doing it. Right. Now, if that angle is not in the unit circle, like it's 7/5 pi or so on, then the unit vector is the cosine of whatever theta is and the sine of whatever theta is. So you might have some decimals in that case. But I think every homework question has been a standard angle, so you'll be able to get it from here. The next thing that we do is we find the gradient vector. And the gradient vector is made up of its x component is the derivative with respect to x, and the y component is the derivative with respect to y. In this case, it's 2x and negative e to the y. And we need to find the value of it at the given point that we're interested in this case 1, 0. So that's 2 lots of 1 comma minus e to the 0. So that ends up being at the point 2 comma negative 1. We're all comfortable with that, what we did yesterday? Now, you put the whole package together and you get the directional derivative, right, u, of the particular function at the point 1, 0. And so that's going to be the gradient at the point 1, 0 dot product with the unit vector direction. So in this case, it's going to be 2 comma negative 1 dot product with that guy there. So root 2 over 2, root 2 over 2. And here it goes. So if you multiply that by that, you get root 2. And if you multiply that by that, you get root 2 over 2. So that's 1 take away a half. So you've got a half root 2. And there, you're finished. So the answer to what is the directional derivative of the point P10 when it touches that surface going at an angle of essentially 45 degrees, the slope of the hill is a positive root 2 upon 2. So you're kind of climbing uphill, about 0.7 units. That's what root 2 over 2 is. So far, so good? Any questions about that process? So let's look at how do you get directional derivatives when the direction is not given as theta is 30 degrees or theta is pi upon 4, but you're getting the direction by being given a unit vector. So you're going to go in the direction whatever u is. So let's show you what that would be. Let's suppose I have a function xy, and it's x squared e to the y. So this is basically a version of question 5. The point that we're interested in is 6, 0. And the unit vector that makes up the direction is given like this. And that's what it looks like in the question. Well, that's not how I'm going to write it. I don't like that notation. I'm going to write it as 4/5 -3/5. Are you comfortable about the IJ notation and the component version, right? That this is him, right? 4/5 I minus 3/5 j. Right. The directional derivative formula then essentially is this fella here. And it's the gradient of the vector at whatever the point is, dot u. So actually, don't we just cut out the middleman? Aren't they just telling us who u is without giving us the angle? So you give me the angle, then I find u, right? You see here, you've got the thing. So all I need to do now is find the gradient vector and then evaluate it at 6, 0. So differentiate with respect to x, you get that. Differentiate with respect to y, you get that. Evaluated at 6, 0 is the next piece. So the gradient vector evaluated at 6, 0 is going to be 2 times 6 times e to the nothing and 6 squared e to the nothing. And that's 12 times 1, so that's 12. And that's 36 times 1, which is 36. So there's the gradient vector evaluated at 6, 0. It's this guy. Here is, they told us, the unit vector. And there's our formula. So the directional derivative of this function at the point 6, 0 is going to be the dot product of the gradient vector at 6, 0 with the u. So it's going to be 12, 36 dot 4/5 -3/5. 12 times that is 48/5. And 36 times that is 108/5. So that makes it 60/5 with a negative in front of it, which I believe makes it -12. And it is. Are we good? I like that technique for getting directional derivatives. Now, as far as I'm just looking at their answers here, they get you to do that answer separately. So that's like question A. They get you to do that guy there, and that's answer to B. And then they get you this fella here, and that's the answer to C. And the other thing, I hope, fingers crossed, I've written the answers, as I always do, using this notation, but they are going to call it 2x e to the y I plus x squared e to the y j, right? So I would hope that it took that as an answer. So I'm going to try something right now just to get that out my brain, so I'm not bothered about it anymore. Is I'm going to go over and we're going to try that question out and see whether or not everything comes out the way I would hope it would. Right. So, well, wrong version. I have to go in as a student going on. So it's going to be, hey, where'd you go? It's going to be view. Hopefully you can hang in there with me for a little minute. That's not the one I want. Okay, do it as a student. In there, open student view. Right. Are you looking at all these? Are these pictures changing? Or am I having to go out and in? Are you looking at WebAssign right now?
Yes.
Okay, that's what I wanted. So there's that fella. So I'm going to click on that. It does mean that they're going to change the question probably, but that's neither here nor there. So here is question 5. Oh, good. It didn't change the question. Great. That means I can use the same answers. So find the gradient of the vector. So the gradient, the way I did it, was square brackets 2x e to the y, x squared e to the y. So let's see how that works. If you click on the vectors, you see you can pick those little triangle systems. And now I'm going to go 2x e to the y. I believe you need to pick e as well, don't you? Yeah, there we go. E to the y. That's the first one. Comma, and then I did x squared. So x squared, back to operations. Where are you hiding? Where's x squared? Help me out here. Where is x squared?
I think you can just use your keyboard.
Oh,
I don't know where it is in the thingy otherwise.
it doesn't have a square button. Yeah. Okay, that was me doing the keyboard, so great. And then we want to do e to the y. And again, I want to make sure that I do that, because if you put in e, it might not recognize it. What are you doing here? I'm not having a good day today. What am I doing wrong? Is it this keyboard thing that I'm doing? Hit a space, put the damn thing in. How hard was it to say e to the y? That's all I was wanting to type in. There. Whew. Okay, I should be able to just hit submit. And if it takes that, great. Submit. And the good news is it will take that notation. But not everybody in the world likes my notation, right? They like the IJI notation. And I have no right, nor would I want to tell you, you must use this notation. So this is how you do the other one. You go 2x squared. No, it's 2x, sorry. Reading too many places here. 2x. We still have to do the e to the y thing. Oh, this time it does it without any hassle. You might think you do this, and I'm actually going to do it wrong. I mean, doesn't that look like the right answer, correct? It's got an I in the giant, but it's not right.
Space in there.
Oh, I've got a space. That's a different kind of mistake, right? That I is not the right I. That's a keyboard I. You have to go to the vectors and do one of those I's. And that J is a keyboard J, not the right one. And you have to do that one. Right. I believe if you did a keyboard I and a keyboard J, it will tell you that you're wrong. So in case you haven't used WebAssign for a while, will you remember that little idiosyncrasy that it has to be a real keyboard I and a real keyboard J? I don't know if it'll allow me to do this, but I'm going to submit it and it should tell me I'm right. Okay, great. Perfect, right? I'm not going to do it with a keyboard I and J. Will you trust me? It'll probably say it's wrong. So be on the lookout if that happens. So we can find directional derivatives of any function you like, as long as you tell me a point and a unit vector that represents the direction. So let's pick another version of that.
Can I see that paper?
There you go. I'm not sure which one I want to do here. I've done that one. Unit vector. Done that one. Any more unit vectors? You can't really see anymore. Okay, this one will do. Let's question it. So the function that we're going to find a directional derivative for is that surface. We're interested in the point 3, 1. And the unit vector that we're going to use is 3/5, 4/5. Just fine. So I'm going to find the directional, the gradient vector first. If you differentiate this with respect to x, you get 1 over y. And if you differentiate this with respect to y, you get negative x over y squared. Are you comfortable about those two answers, or do you want me to show you where they came from? Differentiate with respect to x, differentiate this fraction with respect to y. Are we good with that? Okay, so I can now evaluate the gradient vector at the point 3, 1. So that's going to be 1 over 1, comma, negative 3 over 1 squared, which ends up being a very nice number, 1 and negative 3. I can now get the directional derivative at the point 3, 1. It's going to be the dot product of the gradient vector with the unit vector. So it's going to be that guy, dot product with that guy. And 1 times 3/5 is 3/5, and negative 3 times that is negative 12/5. So the answer I get is negative 9/5.
So I have a quick question.
Yes.
How'd you get negative 3?
How did I get negative 3 here?
Yeah.
3 over 1 squared.
Oh, squared. I thought it was 12.
Yeah,
Never
it
mind.
looks like a 12, but it's just
Thanks.
a 1 squared. We good? Right. That's pretty much it. Would you agree that there's not a lot of difference between what we did yesterday and what we did today? In fact, in a way, there's a little bit less work, because don't we get the u vector for free, right? We don't even need to calculate it. So that's basically that taken care of. Now we're going to look at, well, what do you do when you're being asked to find the directional derivative? And
Sorry.
instead, yes.
Could you put that paper back on the side? Thank you.
So what do you do when they give you a vector v for the direction, but v is not a unit vector, right? So that can happen. So let's pick an example of that. Here's question 9. Suppose I have a function then. It's fractional. The point of interest is 2, 1. And the direction of the vector v is 5, 3. Now they have a couple of clues. The most obvious one is if it's a unit vector, they'll probably call it u. And if it's not a unit vector, they'll call it v or w or some other letter of the alphabet. And secondly, can you look at a vector and tell when it's not unit vector? Would you agree that's not a unit vector? Right. So how do we find a directional derivative here? Essentially, the only extra bit of work is you take this vector, right, this direction vector, and you make it a unit vector. That's all you do. So I find the magnitude of it, which is 5 squared plus 3 squared, which is 25, and 9, which is a square root of 34. And so the unit vector in the same direction of that, but just 1 unit long, is essentially going to be 1 over the square root of 34, 5, 3. And so I'll put the whole package together. And so it's that guy over that guy. Are you comfortable about how I found the unit vector of v? You find its magnitude, and then you divide. Essentially, you divide by that magnitude. We good? Right. So now I'm going to find the gradient vector. So it's the partial derivative with respect to x and the partial derivative with respect to y. Now, as simple as that one looks, I think it's messy. And so I'm going to do it separate over here as some scratch paper. I'm going to find the partial derivative with respect to x. And since there's an x on the top and there's an x on the bottom, that means to me that I'm going to have to do a quotient rule. So we have f dash g take away f of g dashed over g squared, right? And what's that going to get me? You differentiate that guy, you get 1, you leave the g untouched. Minus, you leave the top untouched, and you differentiate the bottom, partial derivative, with respect to x, and you get 2x. And then everybody in the bottom gets squared. If you multiply that out, you have 1x squared plus 1y squared, take away 2x squared. And we leave the bottom as is. And that partially cancels out that. So now I have y squared, take away x squared, all over x squared plus y squared squared. Are you okay with that being the first answer? Now, the other one. Yep, we're going to take this guy. But we're going to do a partial derivative with respect to y. So I'm going to rewrite this guy in that format because I'm wanting to do a chain rule on it. And so when I differentiate it, it's going to be multiplied by the power and reduce the power by 1, followed by the derivative of the inside function with respect to y, which is 2y. So I now get negative 2xy, and that can now come downstairs because of style point rules and look like that. So we have now got the other partial derivative. So this guy here is equal to y squared take away x squared over x squared plus y squared squared, comma, and the other one is negative 2xy over the same thing. We then evaluate the gradient vector at the point 2, 1. Okay, so that's going to be 1 squared take away 2 squared over 2 squared plus 1 squared, which is 5. So that gets me 5 squared. And this guy's going to be negative 2 times 2 times 1, also over 5 squared. And that's going to get me negative 3/25. And that's going to get me negative 2/25. So we've got the gradient evaluated at 2, 1. You put those together, and we can now get the directional derivative at 2, 1. It's going to be the dot product of the gradient with the unit vector direction. So it's going to be a negative 3/25, negative 2/25, with a 5 over square root of 34 and a 3 over square root of 34. If you multiply these two together, you get negative 15 of those guys. If you multiply those together, you get negative 6 over the same two guys. Those get you negative 21 over 25 square root of 24. Technically speaking, I should rationalize the denominator, but I'm pretty sure that won't do any good, really, to make the answer pretty. So I'm happy to leave it alone.
Can't you also take a 4 out of the square root?
Oh, I could do, what would that get me? 4 times 6, that'd get me 2√6. I guess, yes. So
Can you move the
negative 20.
paper up?
What happened to the 34 in the square root?
Is it 34? It was 34.
Oh, so then you can't.
So then I can. Somewhere between here, my brain and my hand, it changed into a 24.
Isn't it supposed to be -3 25th, comma, -4 25th?
Oh, so you think this is a 4?
Yeah.
You're right. What's that going to do? It's going to make this answer 6, isn't it? Let's see. It's going to make this answer here 12, which still doesn't help it look pretty, but at least it's a different kind of ugly. And that's a combine, isn't it? That's going to be a world record today for the greatest number of mistakes in one question. But the fact you're all noticing them is a good sign, because you know all I'm doing is screwing up calculations or misrouting numbers that I'd already written. Okay, I'll try the next one slower. Hopefully reduce the error rate. Oops. Something there. You might have a few fixes to do in this one to get the numbers to come out the way they should. Oh, anything going on here? Too easy. No, nothing there worth talking about. Oh, let's do this one. It's a little bit different. The surface, the function we're going to calculate the directional derivative on is that guy. And we're being asked to find the directional derivative at the point 3, 3. But they're not telling us the direction. They're not giving us theta. They're not telling us u. And they're not even telling us v. What on earth are they going to tell us? They're going to tell us that it's going from P to Q. So can you imagine being at P and traveling to Q? So that's probably the least helpful piece of information that we need, right? Of all of the ones that in this list isn't telling me u the best one, because I don't need to know. If they tell me theta, don't I at least use a unit circle to get u? If you tell me a general vector v, can't I just basically make it a unit vector and we can get it? But in this one, first thing I'm going to do is find the vector. Oops, I'm not calling that. I'm going to find the vector PEQ. So second, take away first. Second, take away the first. That is essentially V. It's not a unit vector. So I'm going to find its magnitude, which comes out as a really nice number, thankfully. Comes out as a square root of 25. So the unit vector that I need, right, the unit vector I need is basically going to be 1/5 the vector PQ. So it's going to be 3/5 -4/5. You agree? It just meant we had to spend a couple of minutes figuring out what the unit vector of direction is, right? Because when we do a directional derivative, the direction has to be as a unit vector, right? Assuming you're told theta is pi upon 4, you know the components you get are a unit vectors, right? They're on the unit circle, they're bound to be. So now I can move on to the gradient vector. And that one, again, even if it looks straightforward, I don't think it is quite as straightforward as that. Okay, I want to differentiate this guy with respect to x. In the format that it's written, I'm very likely to screw up. So I'm going to call it the square root of x times the square root of y. And then I'm going to turn it into x to the half, y to the half. Now, by writing it that way, won't it be just easier to use the power rule? because that's essentially what this is. It's a fractional power rule. So if you want to do the partial derivative with respect to x, multiply by the power, reduce it by 1. And then everything else from this point onwards is style points. Negative power downstairs, 2 downstairs. Square root of y, 2 square root of x. Final answer, that guy. Are you comfortable about the partial derivative with respect to x? Bit messy, agreed. If I'd left it this way, you could probably do it, but wouldn't you have to be really careful? And I'm not sure how careful you could be. It's just very messy. Would you agree that's just more helpful? Right. Now, it is symmetric. That means I should be able to predict Fy without any extra work. I'll take any takers here. What is the partial derivative of this function, but with respect to y this time?
One half root x divided by y.
Agreed. Don't you just switch the x's and y's? So we now have the partial derivative with respect to x. And the partial derivative with respect to y. That's good. And we need to evaluate it at the point that they're interested in, which is at 3, 3. So it's 1/2 the square root of 3 over 3, comma 1/2 the square root of 3 over 3, which ends up being 1/2, 1/2. Wasn't that nice of them to make it come out good? So I should be able to get the directional derivative. There's the direction that we're traveling in as a unit vector. Here is the value of the gradient function at the point P. So the directional derivative of f at the point 3, 3 is the dot product at 3, 3. No, I've seen that. That should be 3, 3 with the unit vector. So it's 1/2, comma 1/2 dot product with 3/5, negative 4/5. 1/2 times that gets me 3/10. 1/2 times that gets me negative 8/10. Subtract them and simplify. And there's your directional derivative. So if you were on the surface of this particular thing, and at 3, 3, you went up and touched the surface, and then you went towards from P to Q, that would be the direction you're going, you'd actually be going downhill at that rate, right? So at that part of the surface, it's you're on the way downhill, not by a lot, but by negative 1/2. So you are downhill. How are we doing, guys? We still okay? Right. So there are 3 different kinds of information that you can be given, and we've looked at all 3 of them now. So I'll do a quick recap before we show you the next little twist in the tail. I can give you a function and tell you to go at the angle 3/4 pi. I can give you a function and tell you to go in the direction of the unit vector, 1 over root 2, comma minus 1 over root 2. I can ask you to find the directional derivative going in the direction 4, 5, or going in the direction from P to Q. Right? We can do it all those different ways. So let's do something a little bit different. Blah, 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 blah. Increase the number of variables. Right. So what this would represent is something you couldn't draw. It actually represents a fourth dimensional situation. See, this is a point in 3D that travels into the fourth dimension to touch a surface that looks like this. And this would almost certainly be an example of a hypersphere. You just take the word hyper when you leave 3 dimensions, right? It's the surface of a sphere in 3, but if you move into 4 dimensions, because that's a z equals, it would be a hypersphere, or at least something related to that. Nonetheless, we can still find directional derivatives. So we can actually do calculations beyond the number of dimensions that human beings can perceive. And if you're into physics, as strange as that may seem, those people, astrophysicists and so on, are quite comfortable with the fact that to describe the universe, you do need more than 3 dimensions. A lot of people, for instance, know that if you do space-time, isn't the universe 4 dimensions? 3 location, 1 is time. But in string theory, I think you need, I think it's 11 dimensions. So the universe is described with 11 dimensions, right? 3 of which will probably be where you are. 1 of them is when you are, and who knows what the other 7 are telling you, but evidently you need them. So how do we do this, guy? Well, we need to find the gradient vector. The cool thing is that once you know how to do it in 2, 3, or 40 dimensions, once you know how to do it in 2, you can actually move on beyond that. What do you think the formula, or the vector formula, for the gradient of this guy is going to be?
F of x, then the f of y, then the f of z.
Or z even, yes. Isn't it nice that, so can you see that the string theory people like us because isn't an 11th dimensional gradient vector no more difficult than a 3-dimensional or a 2-dimensional one, right? So what would this one look like? Well, I've made a very symmetric one because I wanted to make this question nice and simple before we do anything too crazy, which is that. And then I would evaluate it at 1, 0, minus 1 in this case. So 1, 0, minus 1. And that would get me 2, nothing, negative 2. And now we need to find the directional derivative of this function, right, at the point 1, 0, negative 1. Well, there's the gradient and there's the unit vector. The formula does not change in any meaningful way. It's the dot product of the gradient with the unit vector of direction. Isn't it nice? Nothing changes, essentially, right? So we're going to do a dot product of 2, 0, negative 2 with 1 over root 2 minus 1 over root 2, 0. And 2 times that guy gets you this fella. Nothing times that gets you nothing. Negative 2 times 1 get nothing. There is your answer. Now, unless some of you have got a better brain, and I'm not saying you don't, than I have, I cannot tell you what a slope in 4 dimensions looks like. I can just about imagine being on the surface of a 3-dimensional world, right, and going in a certain direction, and therefore I'm increasing, you know, I'm kind of, for want of a better word, I'm going upwards a little bit. Matthew.
Wouldn't that answer just be root 2?
Oh, as a simplified version? Yes.
Yeah.
In fact, that would be a good example where it is worthwhile to do the rationalize the denominator.
I have a question.
Yes.
Up on where you wrote the u value, is that a negative for the y value,
Yes.
or is it?
It's a
Okay.
negative.
Gotcha.
Isn't it kind of fun that you can now do directions in 40 dimensions if you felt like it, and have surfaces with 32 dimensions if you wanted them to? You'd have a really hard time imagining them, but apart from that, life is relatively straightforward. So for our final question for today, and when I see you on Monday, we'll finish off directional derivatives. Here is our function. The point we're interested in is all the 2's, and the direction is a vector v called that guy. Okay, is there anything here that we need to fix? For instance, is v really the vector that I want to use when I do my equation, my formula? No. So
No,
one,
we
I
need
have
to
to
make that
find
into a unit
the
vector.
unit vector equivalent to it. So let's do that. I am hoping upon hope that that ugly number ends up being a really nice number when you do it inside the square root. But there's no guarantees in the world. So let's just do it as a calculation first. 6 squared plus 18 squared plus 9 squared is 441. Oh, interesting. And the square root of 441 is 21. Isn't that why you use textbooks to make up questions? Because if I'd made up a question, wouldn't that be the square root of 392 or something? That'd be no good to nobody, right? It'd be really ugly. So our unit vector is essentially going to be 1/21 of v. So 6 over 21, 18 over 21, and 9 over 21. And if that wasn't good enough, they even made it, I'm not sure if they tried, but they made this guy divisible by 3. So that's 2/7, 6/7, and 3/7. Okay. Now I need to find the gradient vector. Well, the variables are in the order r, s, and t, so that's pretty clear what order I need to do the derivatives in. If you differentiate this guy with respect to r, you get 1 over 3r plus 6s plus 9t. Agreed? But don't you also get the derivative of the inside function? And with respect to r, isn't that going to be 3? So are you happy about if you differentiate this with respect to r, that's the fraction that you get? Are you comfortable with that? Right, I'm going to do a little bit of cheat here. 6 over that fraction and 9 over that fraction. Those dots mean this thing. Does that seem reasonable based on what we did the first time? Now, it's not quite symmetry, but isn't it kind of common sense that you're going to get the same answers, same looking answers? Now, if you want to do the gradient vector at the point 2, 2, 2, you're going to do 3 lots of that is 6, 2 lots of that is another 12, that's 18, and 18 and 18 gets you 36. So you're going to get 3 36s, 6 36s, and 9 36s, which is 1/12, 2/12. I know that's a quarter and that's a 6, but I'm going to leave them as 12ths. And the reason I'm going to do that is if I'm going to multiply, it just makes fractions easier if they're all sharing the same denominators. Agreed? Anything wrong with that? Are we good? Okay, move on. The directional derivative of this surface at the point 2, 2, 2 is the gradient at 2, 2, 2 dot product with the unit vector of direction. So I'm going to do a 1/12, a 2/12, and a 3/12 with a 2/7, a 6/7, and a 3/7. Right, that guy times that guy gets you 2/70 That guy times that guy gets you 12/84. And that guy times that guy, I believe, gets you 9/84. So that's 1423/84. Barring the fact I can't count, I hope that's correct. Any obvious mistakes?
Can you
None
move
we
the
can see.
paper up a little bit?
Sure. Right. Well, while I'm getting ready for this last piece of things I want to talk to you about, why don't you do attendance? So put just your last name, please, for attendance. Okay, I'm ready to show you then. I want to figure out what button I should be pressing, I'll tell you. There we go. So you should be looking right now on the screen, and what you're seeing here. What the heck's that? Never seen that before. Anyway, you've got partial derivatives and chain rule. That's what's due this midnight Sunday. Your online test one now is visible. And oh, good. When you do that test, or when you're ready to do that test, make sure that when you click in it, that you start doing it, because the clock ticks and your time will go, and you only get one shot at it. So don't waste it. If you have problems finishing your homework, you email me at drobertson@olympic.edu and I'll give you an extension. And that won't be a problem. But you will lose your participation point for doing homework on time. So if you don't want to lose that, then you know, don't ask for any extension. You don't get extensions on tests. If they're not done by midnight Sunday, they're not done. You're allowed to drop 2, so I guess that'll be one of them. That's about it. Any other questions before we call it a day? Oh, you don't need to, but I would suggest strongly that if you've got time, that you do as many questions from 14.6 as you can, so that next week you'll have a lot less homework to worry about. So that would be my advice, but you don't need to do it. It's not due until a week on Sunday, so it's not like it has to be done. Okay, bye-bye, guys. Have a nice weekend. I will see you on Monday, bright-eyed and bushy-tailed, right? Including you, Matthew, so get sleep. Dylan, what you got? What's your question?
I believe it's question 13 on 14.5, but I just need to double check.
Okay, 13.5. 14.5. The chain rule ones.
That would be the one, but
Okay.
I'm gonna check to see. Yeah, it is 13.
All right, and I'm clicking in it as we speak. Let's have a look at it. Okay, so what did you do wrong, if anything? You're 90% right, but your signs are wrong. In other words, some of your signs are different. They're pluses when they should be minus, or they're minus when they should be a plus.
Yeah, I don't know if you could see how many times I've tried, but I knew something was wrong with the signs, but I didn't know which one. So there's a few different renditions that I put in.
Okay, I'm going to show you one of those. Well, not one of those. I'm going to show you the rendition that it was looking for, and maybe
Okay.
you can say, "Oh, well, I see what's going on here." Right now, the one that you've got here, you've got a negative there, but if I push that negative through all the terms, all that will mean is that this one here is going to be correct, and this one here is going to be right, but that and that one will be wrong. So
I don't distribute.
you're
Do
not
I?
distributing well.
Just stick it. Okay.
Right. Okay, so you want to stick a negative on this one and make them plus and plus, and put a negative on this one and make that a plus.
So in the equation up top, the f of
Uh-huh.
x over f of y, when you have the answer, you do not distribute the negative.
I
over
would
one of them.
distribute the negative. So
Okay.
I'll show you. What might be the problem is that distributing the negative is something that's not that common, and so you may not do the algebra properly. So let's suppose we got the classic fraction story, right? Just making up whatever, right? Right. Now, technically, that's the answer, correct? Right? It's a negative of whatever it is. Now, when you distribute it, basically, you only do it to the top. What a lot of people think is that the distribute is going through top and bottom, but technically speaking, you only do it through the top. And so if you want to think, well, why is that the case? It's really this guy that you've got.
Yep. That's pretty much what I did. I think I may have just accidentally dropped a few signs while doing the algebra. So
Okay,
I'm gonna go look back through.
Right, so you've definitely got all the pieces, right? All the e to the y's and the sines and the cosines, and they're all in the right place. So you haven't put an x in the top when it should be in the bottom. So the only thing you've got to do is get your signs sorted out. So it's a negative 4e to the y, and then a plus y plus 1. And on the bottom, it's a positive 4e to the y sine x, right? With a minus x. So if you look at your last one that you did, you only need to take the brackets away, and you only need to change the plus x to a negative, and the top, make that a negative 4e to the y cos x, and leave everything the same, and it will be fine.
Okay, and wait, why should I not distribute on the other one, or was that already accounting for it?
Yeah, if you did it to both, what you're essentially doing is that, which means that you're not doing anything, because that's one.
True. Okay, that makes sense. That's just one.
Technically speaking, if you're being really awkward about it, you could distribute it on the bottom and leave the top.
Oh,
And
so
that
I could
would be-
choose?
Yeah.
Oh, okay. That's a big
I
help.
wouldn't, but mathematically, you could.
Yeah. I will. That solves the problem. Thank you so much.